So if we're in our good old base 10 car, base 10, meaning, or called decimal, it's got the digits 0 through 9. Like I said, I'm really not expecting y'all to type along with me. And so if you start cruising along, it looks like this. Wait, no, I start counting in binary. Old habits. All right. Etc. Right? And then, you know, by the time you get to 9, it rolls over. By the time you get to like 99, it rolls over. So what are these different columns? Well, since we've learned from grade school what they are, we know them, you know, instinctively. We don't even have to think about them. But that's the ones column. The first column's the ones column. The next one's the tens column. The third one's the hundreds column. So if you have this number, if you have 349, that's 9 in the ones column plus 4 in the tens column plus 3 in the hundreds column. All right. So why are they 1, 10s, and 100s? Where did those numbers come from? This column here is 10 to the power of 0. That last column is 10 to the power of 0. Anything to the power of 0 is 1 through some little mathematical proof that I might be able to come up with if I had to, but just trust me. 77 to the power of 0 is 1. Negative 77 to the power of 0 is 1. Everything to the power of 0 is 1. Okay, and then this next column is 10 to the power of 1. And then this next column is 10 to the power of 2. So 349 is equal to 3 times 10 to the power of 2 plus 4 times 10 to the power of 1 plus 9 times 10 to the power of 0. Or restated, this is 300 plus 40 plus 9. Now, look at that. We're so clever, we converted from base 10 to base 10. Okay. So, but the same idea carries over to powers of 2. If we have 1, 1, 1 here, but we're talking in binary, this last one is 2 to the power of 0. This one is 2 to the power of 1. This one is 2 to the power of 2. And this is a healthy helper crib sheet. That's a 4. That's a 2. That's a 1. And if we kept adding numbers, it'd keep doubling each time. Right? 8, 16, 32, 64, and so on. So if we have the number 111, that's equal to 1 times 2 to the power of 2, or 4, plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 0, which restated is a 4 plus a 2 plus a 1. Now writing out like that's a little bit tedious, right? And so a 4 plus a 2 plus a 1, if we added all those up, is a 7. So this 111 here in binary means 7. And if we counted it out, we would see the same thing. If we saw this, we're going to say that this is the 4's column, this is the 2's column, and that's the 1's column. Keep with me, guys. I know math is boring. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, how many different numbers did we count there? 8, right. 2 to the power of 3. 8 different choices. And so all zeros adds up to 0. 0, 0, 1, well, that's no 4s, that's no 2s, but there's a 1 there, so that's a 1. 0, 1, 0, there's 1, 2, and there's no zeros, so that's 2. There's a 2, You see? And then there's a 1. So that's equal to a 3. What is this equal to? That's a 4. And this one? Okay, it's kind of obvious because it's increasing by 1 each time, but it's a 4 plus a 1, which is a 5. And so this is a 4 plus a what? 4 plus a 2, and then the last one's going to be 4 plus 2 plus 1. So each 0 or 1 is called a bit. That might be worth typing down. 8 bits in a row is called a byte. The byte is the smallest addressable unit of memory in a computer.
Did you want to?
Pardon me?
You want to like type in the three quotation marks first?
Oh, you don't need to do any of this. So there's each 0, 1 is called a bit. 8 bits makes a byte. If we had 8 bits, every value in that byte can be a value between 0 and 255. Each byte can hold one of 256 different values. So underneath it all, everything we type gets saved as numbers. They're saved as 0s and 1s, but when it gets written out to the computer's memory, they get written out in clusters of 8 bits. The system that is used to convert English text into numbers is called ASCII, A-S-C-I-I, which stands for American Standard Coding Information Interchange, something like that, whatever. Text stored as numbers. And even though it's the American standard, everybody wound up using it just because. There's a problem with the idea of ASCII, though. But ASCII kind of works. It worked just fine up until the 90s. What does ASCII mean? If I go here and I type in ASCIItable.com, ASCII, that's A-S-C-I-I, table.com, we see this thing. And by the way, this stuff existed actually, it predates computers themselves. Well, why in the world? Do you remember like in the old movies where you had Cary Grant and Katharine Hepburn and they were sitting there at the teletype machine? I'm kidding, I don't know if there was ever a movie like that. Or at a ticker tape machine. You had to have some way of sending information from New York to LA so that the newspapers could get it over a phone wire. And so the way they did it is that each series of pulses meant a different letter. Don't know if any of y'all have ever even dialed one of those rotary phones, but you know, if you pull the thing to a 7 and you let it go and it go deep, and make 7, right? It would dial big 7 pulses, and the phone company knew that you dialed a 7. And if you were going to call a 3, you dial it up to 3, and you let it go and it pulse 3 times, and that was a 3, and so on. Well, to do all the letters, you'd have to have like 26 different options, right? A through Z is 26. You need all the numbers, 0 through 9, so that adds 10 more, that might be 36, plus a good handful of punctuation, right? Maybe in olden days they left off the punctuation. Maybe everything could be, but you need a character for spaces, right? If you didn't have any spaces, it looked pretty weird. So that's 37 plus, you know. So anyways, if you do only uppercase letters, you could store everything using 6 bits. I don't care if you keep track of this, but I'm going to type it in. So if you have 2 to the power of 6, that's equal to 64. So that's enough for all the lowercase letters. Seems like it'd even be enough for the uppercase. But let's think it through. 26 plus 10 is 36, plus maybe some punctuation. 10 characters of punctuation is 46, plus a space, plus if we looked at this ASCII chart, we're going to see that there are a whole bunch of control characters, right? When Katharine Hepburn was getting her teletext or her, her teletype, whatever, ticker tape, the start of the text, it was preceded by a number. There was a character that could be sent to ring the bell, a character that could cause a backspace, tabs, hitting the enter key. All of these are called control characters. And then some of them can get pretty cryptic, right? I don't know what any of these mean, but you press the shift key and then you release the shift key and stuff like that. So everything your keyboard types, every time you press a character on your keyboard, it gets turned in to a number or a series of numbers. So here's our ASCII table, and if we wanted to type in the word Python in all caps, here's what it would look like. Python. I would look it up over here. Going to ASCIItable.com, I know these letters aren't small and you're not going to be able to read them, so just trust me. A capital P is an 80. A capital Y is an 89. So we'd have 80, 89, a T. These are all just in sequential. So once I memorized one, I could figure out the rest of them. But the only one that I have memorized is A, which is 65. And I can't, I don't know the difference between a T and an A in my head. So anyways, so that T is an 84. And an H is a 72. So 84, 72. And an O is a 79, and an N is a 78. All right, so that would spell out Python. And then if I was going to hit the enter key, there'd be a special symbol called a new line. Not going to add the new line in. Okay, there were a lot of columns here. Hex. Oct. Well, that stands for octal. Like I said, we're not going to ever use octal. But we have decimal, we have hex, and we have octal. Some of y'all have heard of hexadecimal. Majority of you probably have not. Don't know if I want to get to hexadecimal yet, but it's interesting as much as, yeah, I'm going to demonstrate it. Well, I'll go ahead and talk about it. But firstly, go ahead and pull up Word or Notepad or something like that. Get some kind of file going. And I'm going to give you an example. Say we have 5 bits going on. And the place values are 16, 8, 4, 2, and 1. Those are the 5 values. And so if I have this number, but I'm going to space it out to make it easy.
Does it need to be spaced, or can it just be like 16 equal to 1 without any spaces?
However you want to, however makes sense to you. So if you have these numbers, what is that up to? This adds up to a 4 plus what else? Here's our 4. Are there any other ones in our number? The 1 column, right? And so that's a 5. Now I'm going to make one more, and then I'm going to want you all to do some. So what is this equal to? What's the first bit counting from left to right? What's the highest value here? 8. And then what's next? And then plus a 2. So then 8 plus a 4 plus a 2. By the way, if you get this part right, even if you don't do the last little bit of math right, I'm going to know that you have the concept. So, if you added that together and you got 11, even though it's not 11, that'd be okay. All right. So, just on your notepad, I want y'all to do kind of the same thing here. I don't care if you type in these numbers. These are just for convenience. But I want y'all to tell me what these numbers add up to. Those 3. Same way. All right, this first one. What's the highest bit? What's the leftmost bit? If I was going to start typing them off across here, I should give y'all more time. I'm sorry. So what is this place right here?
16.
That's a 16 plus.
8.
Are there any 4s?
No.
Nope. So there's a 16, 8, and a 2 and a 1.
That's 27.
I trust you. 16 plus 8 plus 2 plus 1 equals 27. Looks like all of these have 16s. So that's a 16. Are there any 8s?
Yep.
Any 4s?
Yep.
But there's no 2s and no 1s. 16 plus 8 plus 4 is 28, I believe. And so this last one, are there any 16s? Yes, indeed. Are there any 8s?
No.
What's next?
4, 1.
And then after that?
1.
Yep, cool. All right. What if you had to go the reverse? I'm never going to ask you to do this. But say you, maybe I'll just write it over there. Say you had the number 400, now let's not get overzealous. 43, and you wanted to turn that into binary. Here's how you do it. Okay, here's one way to do it. This is how I did it before I learned that there was a process. I learned all my powers of 2, and I said, okay, are there any 32s in 48? Yeah, there is. And 48 minus 32 is 16. Okay, are there any, and I just kept going places and subtracting and trying to, yeah, there's a process for doing it. So if we have 43, what you do is you divide by 2 and you keep track of the remainders. So 43 divided by 2 is, well, 2, 1 with a remainder of 1 because it was an odd number, right? So these are our remainder. This is our modulus column, whatever we want to call it. All right, now 21 divided by 2 is 10 with a remainder of. Is 10 an even number or odd? So when we divided it by 2, was there a remainder? I'm sorry, maybe I lied. 21, I totally botched that one. 21 divided by 2 is 10 with a remainder of 1, right. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. And then 1 divided by 2 is 0 with a remainder of 1. And so we have this series of zeros and ones, and you actually, although you might think that you start from the top, you write it down. So 0, 1, 0, 1, 0, 1, 1. And if we added them up, we have a 1 and we have a 2, we have no 4s, we do have an 8, we have no 16s, and we do have a 32. If we added all those up, it equals 43. And I'm not, like I said, I'm not going to ask y'all to do that, but that's how. If you had to take one number and convert it, you could. There's certainly easier ways, right? You find an application to do it for you, right? Binary conversion, binary calculator, something like that. Alrighty. Well, that's not exactly what I was looking. Even the basic app that comes with Windows, if you look at the calculator app, it's got some modes over here that'll get you like a programmer calculator, let you type in numbers and zeros and ones and stuff like that so you can do some conversions. I don't care about that. Like I said, if I ask you to convert 11100, I don't want you to tell me it's 28. That's not the right answer. The answer is to write down 16 plus 8 plus 4. If you got that one right, I don't even care if you add that last one up correctly. So I probably ought to come up with an itty-bitty short little quiz based on that and post it online. I'll try to remember to do that so that y'all can actually get some credit for knowing this stuff. Okay, so say I was looking at a page full of binary numbers. My eyes would start to roll up into the back of my head. I don't know if this is going to pop up anything. Yeah, like that. You go, okay, Mr. Computer Scientist, you tell me what's going on there. Well, there's really no way that I could remember these numbers. There's no way that my mind could interpret them. So, what people do, or what people did, so that when this information was printed out, it had to make a little bit more sense than just being zeros and ones. Now, you could convert it just like we were doing into decimal numbers, right? There's kind of a problem with doing decimal numbers for this purpose, and I'll show you what it is. Say I had this data here. I'm just going to totally, but I'm going to add spaces even though there wouldn't be spaces on the screen, right? In order to make this easier, why don't we create just a little chart showing all the numbers between 0000 and 1111 and what they mean in decimal. So 0000, 0001, I don't care if you'll type this, 0011, 0100, 0101, 0110, and 0111. And then there's going to be another series that looks just like that, except they're all going to start with a 1. But anyways, that's a 0, right? That's a 1, that's a 2, that's a 4. Wait, what am I doing? That's a 3, that's a 4, right? All we're doing is counting. 5, 6, can I type? 7. Or we could back check ourselves, right? No 4s plus no 8s, 1 4, 1 2, 1 1 is 7. Okay. And then we have to do the same thing. And by the way, if I ever ask you on an exam or something, I think I've done something wrong. Yeah, what did I do wrong there?
Should be 1111.
Yeah, this one should be 1110, and so the next one should be 1111. All right, and so this is an 8, right? Because the 8's column is lit up. If we did 8, 4, 2, 1 on top of it, we'd see that that's the 8's column, and this is a 9. That's a 10, 11, a 12, a 13, a 14, and a 15. Like I was about to say, I'll never make you waste the time to type this or write this down yourself so that you can do what I'm about to do. Okay, so I have all those numbers, and I'm just going to do a simple lookup here, and I'm going to write these numbers down. A 0011 is a 3, and a 1111 is a what?
15.
That's a 15, and so we have a 0101. That's a 6, is it? No, that's a 12. That's an 8. That's a 4. I should stop winging it. Thank y'all. All right, that's a 15. I got that one. And a 0. Okay, there we go. So, and then if we just strung all these up together, right, for display on the screen. Can we take all the spaces out? Not really. We can't take all the spaces out because we don't know whether, you know, that was a 1 followed by a 5 or a 15. So what we would have had to do in order to get that to work is we would have to pad them out to 2 columns like this, right? But there's a more efficient way of doing that. This meant that every 4 bits on here got turned into 2 numbers to be shown on the printer or shown on the screen, right? Those 4 bits got turned into those 2 numbers. These 4 bits got turned into those 2 numbers, and so on. Well, what somebody decided is that you could have a counting system where you didn't just stop at 9, but you had another digit for that one, 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 another for that one, and another for that one, so that you could count the entire system 0, 0, 0, 0 to 1, 1, 1, 1 with only 1 digit, rather than having to roll over and have 2 digits. And so they call that hexadecimal. Hexadecimal. You know, hex like a hexagon is 6, and decimal meaning 10. So that's a counting system where you have the digits 0 through 9, but you also have an additional 6 digits represented by letters, plus digits A through F. Now, it was just A through F because it was invented, you know, in the United States, maybe England. I don't know who invented hexadecimal. But, you know, if this had been, if the Russians had invented it first, the first 6 letters of their alphabet would have been used as these letters. So if this is the binary number, and this is the decimal number, then this would be the hex number right there. They start off the same. Right, nothing's different until you get to the point where our counting system, something looks weird there. Oh, all right. And so this is continuing the binary system. This is still the decimal value, and then we have some hex values. So an 8 in hexadecimal is 8, a 9 in hexadecimal is 9, and here's where it starts looking a little bit weird. A 10 is an A, an 11 is a B, a 12 is a C, a 13 is a D, a 14 is an E, and a 15 is an F. So if I had these digits here, and I wanted to write them down in hexadecimal, well, instead of a 3, well, it's still a 3. And then that's an F. And that's a 5. And what's a 12? A 12 is a C. And that's a 4. And what is a 15? That's another F. And that's a 0. So if we copied and pasted those and removed all the spaces, then we were able to display it on the screen in half the space, right? Did not take that many spaces on the screen to change our zeros and ones into something that we could look at. Instead, look like that. This is a very common representation of numbers because you can do a one-to-one correspondence in your brain. I mean, if you look at this long enough, right? I can't do it. But between these letters and the bits that represent them, we could work backwards. If I had this number, A9B03, it'd be real easy for me to look up backwards and go, okay, well, what's an A? An A is a 1010. Where'd my digits go? Right, an A is a 1010. And then what's a 9? We're doing reverse lookup here. A 9 is a 1001. What about that B? 1011, and a 0 is 4 zeros, and a 3 is a 0011. Right. So if you stared at this for a year, a month, whatever, you know, and you would very quickly learn, you know, this table inside your head, and you could look at it and you would just pretty much know, you know, just like we know our own counting system, right? We know that 3 times 9 is 27, and we know that as we add 9s, the numbers, you know, well, maybe we don't, right? But if you have 1, 8, and then 2 times 9 is 18, 3 times 9 is 27, 4 times 9 is 36, and these digits always add up to 9, right? 1 plus 8 is a 9, and a 2 plus a 7 is a 9, and a 3, 6, right? The longer you look at things, the more you know patterns. So anyways, that's hexadecimal here. Hexadecimal works just the way that decimal and binary works. If you were converting, if you had this number 1, 0, 7F. That's going to be a little bit hard for my brain. AF, 10AF in hexadecimal. So that's base 16. And I wanted to convert that to a decimal number, a number that you and me like, rather than this. Not doing it by converting to ones and zeros, although we could do that, right? We could write out one great big thing like that, and then we could say, okay, well, that's a 1, and there's a 2, and there's no 4s and no 8s and no 16s and 32s, but there is a 128 and there's a 250, right? That's a little bit hard. Instead, it's powers of 16 rather than powers of 10 or powers of 2. So we have 10 to the power of 3, 16 to the power of 3 in this column, 16 to the power of 2, 16 to the power of 1, and 16 to the power of 0. Well, anything to the power of 0 is 1. Anything to the power of 1 is itself. And 16 squared, I just happen to have memorized. I think it's 256. 16 cubed, you'd think I'd have this memorized. 16 times 16 times 16 is 4096. And by the way, we'll never do this much math again in any other lecture. So there we go. We have that. These are our place values, and we're trying to convert 10AF into some decimal number. So I'm going to write them down into this place value here. 10AF. Okay, so if we were going to add them up, in this column, in the 4000s column, we have 4096. Do we have anything in the 256 column? No. Do we have anything in the 16s column? We have an A, and if we looked up here, an A is the same thing as a 10. So 10 times 16 is 160. Plus, what's our next column? We have, in the ones place, we have an F, which is a 15. So that's 15 times 1. If we were going to write this, 4096, which I guess I should have written as 1 times 4096, just to be precise. 4096 plus, come on, plus 10 times 16 is 160, plus 15 times 1. And if we added those up in our head, which I can't do, we would get what the conversion really was. I love Google for math. You just paste a little equation up here and it tells you the answer. Okay, so that's 4271. All right. I really will give y'all a little worksheet based on this. Maybe we'll do it after the break. Just because I want y'all to have some experience of multiplying these numbers together to get that. But for now, we're just going to accept that we have a counting system called hexadecimal, which uses extra digits, letters. And the reason we do that is to match the binary more conceptually. Oh, by the way, that was the whole purpose of octal. I kept mentioning octal. If you took this series of bits here, you could break them up into clusters of 3 rather than 4, because 3 bits gives you 8 different values. and you would go, okay, well, that's a 1, and that's a 7, and that's a, I don't know. Anyways, and so you could write it out again in octal, but we're not going to bother doing that. Okay, so we have our hexadecimal car. We're going to hop in our hexadecimal car. 0, 0, 0, 1, 0, 2, 0, 9. Okay, we've driven another mile. Is it going to flip to 10? No, because this is hexadecimal. We can keep adding in the ones column. 0A, 0B, 0C, 0D, 0E, 0F. Now we have maxed out, right? There's no letter G in hexadecimal. It's A through F. So now it rolls over. And what does it become? Well, the maximum is an F, the minimum is a 0, and so it rolls back over to being a 0, and we add 1 to that. So that's how you count, if I hadn't skipped some, right? That's how you add up, excuse me, that's how you count from 0 to 10 in hexadecimal. And up until this point, they're all just the same, right? But we decided that an A was a 10, that's an 11, that's a 12, that's a 13, that's a 14, that's a 15, and that's a 16. And if we kept going, we could get all the way up to FF. And then if you drove 1 more mile, you all have the idea of rollover, right? You rolled over your car at, 1,000,000 miles. You drove 999,999 miles, and then it flipped all back to zeros on your odometer. Same thing here. If we didn't have any more information and we added 1 more to it, it would roll back to 0. So anyways, now that we have these digits, we can understand one more thing about the ASCII table. Which is that there was this column here, and we spelled out the word Python in hex, but we can also spell it out in ASCII. I wonder if I can pull this over here, get my notes over here. So if I have the word Python, and I wanted to write it down in ASCII, but use the hexadecimal column, that P is a 50. That Y is a 59. You see how I'm doing this, even if you can't quite see the letters. A T is a 54. An H is a 48. And an O is a 4F. And an N is a 4E. Alrighty. So these are the ASCII values represented in hexadecimal. If I save this notepad and then I view it in what's known as a hex editor, then where the word Python was, I would instead see these numbers. Well, we can kind of do that. There's a website called a hex editor that we can play with this kind of stuff. Open up Chrome or IE or Firefox or whatever you like and go to hexedit, HEXEDIT.OR. I don't know what world OR represents, on the internet. How like.ch represents China, .uk represents England. I'm not sure what .or is, but hexedit.or takes you to the... Oh, my mistake. It's just hex, HEXED .it. I do know what IT means. Italy. Hexed.it, and it takes you to this page. So, if I type those numbers in that I just calculated over here, like if I go here and I type in a 50595484F4E. You see what it did? It spelled out the word Python. These are the ASCII values, and these are the English values. The the text representation of that. So you could come over here and you could type in your name, you know, Bugs Bunny. Now I didn't talk about lowercase letters, but lowercase is just another column on that chart, right? And so these are the hexadecimal ASCII values for this text, bugs.bunny. If you have hexed.it open, go ahead and click Open File and choose one of your Python programs and upload it. Just any of them. It doesn't matter which one. Lecture A.py. There it is. Here's my program. This is all the ASCII text. And you see where I wrote out my name, Lecture A, and my name, Jeff Thompson. Well, that E there, I could change that to like an I. If I knew the ASCII value of I, honestly, I could just type right, you know, an I right here. But the ASCII value, well, I'm just going to change this Lecture A to make it say Lecture B. And so that 41, I'm going to change that to a 42, and I'm going to save my document. So instead of saying Lecture A, whoops, I goofed. I meant to type 42 right there, not on this side. So where it says 41A, if I change that to 42 there, it changes that to a B. And if I save my file, I guess it's called export. And then I go and edit that file. I'm going to see that it now says Lecture B rather than A. So I use the hex editor to change the actual bits of my file, and the result of it was to change that A to a B. So a hex editor is actually kind of a useful thing if you wind up being at the point where you need to look at the zeros and the ones and the ASCII values and stuff like that stored in a file. You can look at any file with a hex editor, not just a text file. But now you've heard that phrase, text file. What is a text file? It's a text file where all the values are in the ASCII table. And you just convert, the computer just converts those zeros and ones into the text in that column. And then when you hit save, it saves all that English text, all those typewritten characters into that format. Now, is that the only format for saving data? Is that enough of a format to get away with everything we want to do? Well, no. For one thing, what if you're German and you have lots of characters with diacriticals and umlauts and stuff like that, or you need the Spanish with the N, or the upside down question mark, or Russian, which uses a completely different alphabet, or then you wander off into the non-European languages, kanji, Japanese, or whatever, where you have 1,000 or 2,000 or however many different symbols, right? The ASCII table is completely inadequate for holding all that information. And yeah, there's a Russian version of the ASCII table where the English characters are substituted to Russian, right? Same for German and stuff like that. It used to be, if any of y'all were old enough to have a computer installed in your crib and you went to a web page on the internet and it was in Russia, then you had to choose from an encoding menu in your Netscape browser or whatever. And you said, no, this isn't English. You'd switch the encoding menu to Russian, and it would use a different ASCII table to show the characters all in Russian. Otherwise, it looked pretty much like garbage. Of course, since I don't speak Russian, it still was incomprehensible, but at least it didn't look like pure garbage. And so on. And then you could choose the Russian encoding and the Japanese encoding, whatever, and it would try to turn it into text. And nowadays, all that's handled automatically. Right? Whenever you go to the web page, unless there's something drastically wrong, it just displays it just fine. It figures it out. But if you have all those alphabets, right? If you have French and German and Italian and Spanish and Czechoslovakian and Russian, I know there's a better term for the Russian alphabet than just Russian, but I can't pronounce it, Cyrillic or something like that. Right? That's a lot more than 256 different possibilities, which is all that a byte can hold. 0 to 255, 201 to 250. The letters involved in that adds up to a lot more than 256 different choices, especially once you start getting to the non-European languages, right? Korean. There's a North Korean alphabet. There's a South Korean alphabet. There's, you know, the more than one version of written Japanese. There's, you know, Chinese, and so on. Huge, huge, huge numbers that in no way could they be stored in some counting system where you only had 256 different choices for letters. And so the people who needed to created something called Unicode, where you had 2 bytes dedicated per letter. So you didn't only have 8 bits, you had 16 bits, right? Each letter would be stored as a series of 16 bits. That holds a lot more than 0 to 255. I think that holds about 65,000 different values. So 65 different thousand letters, that's just about enough for all the languages. Even emoji, right? You know, your poop emoji or your gun emoji or your, you know, your angry face, your sad face, your whatever are stored as part of the Unicode system. So, you know, it has to be large enough to hold them all. So, just for grinsies, if we were going to play it with our 8-bit Nintendo or whatever it was, the number of colors that it could display on the screen might have been a maximum of 256 different colors, because that's 2 to the power of 8. So an 8-bit machine could have done that. Then you bought your Super Nintendo or your Genesis. It was a 16-bit chip, and so 2 to the power of 16, why don't I just let Python tell me what that is? 2 to the power of 16, 65536. So it could just pick from a much larger palette of colors. And also the screen resolution was increased because it had, you know, a video card with a higher number of bits, right? So it could represent, you know, not just 256 pixels wide like the Super Nintendo, but maybe 512 or something like that. Then you bought your PlayStation, and I don't remember where the PlayStations were 32 or 64 bits. Let's pretend they're 32, because until recently people were buying Intel computers that were, you know, 32-bit. You had a 32-bit version of Windows in it. So if you have a 32-bit version of Windows, that's about 4 billion. The Windows operating system could, if it was a 32-bit version, access a maximum of 4 billion different bytes. So if you bought a laptop that had more than 4 gigabytes in it and it was running the 32-bit version of Windows, then it would not just be able to access that as you know, as contiguous RAM. It might have some other purpose, maybe it caches data in it with the extra whatever. But anyway, so 4 gigabytes was effectively the most RAM that a 32-bit operating system like Windows could access. But then came the 64-bit chips and the 64-bit operating systems. And so 2 to the power of 64 is just a gigantic number. 2 to the power of 64. All right, so when I said disk, I meant RAM. 4 gigabytes of RAM. 4 gigabytes of RAM was the max that Windows could access for your software. And if you had more RAM in your laptop, it did something else with it. Okay, but this is a lot. That is a huge amount of RAM. I can't even figure out what that is. You know, in billions and millions and whatever, that is just a huge number. So that's the thousands place, that's the millions place, that's the billions place, that's the trillions place. I don't even know what's after trillion. There, okay, 18 gazillion, whatever. It's going to be a while before you're able to buy, you know, a RAM chip to install in your laptop that holds 18 gazillion, you know, bytes of RAM in it. So what does giga and mega and all that stuff mean? It's, if you've ever taken physics or chemistry, you're used to kilo, like kilograms. If you're Breaking Bad and you're selling, you know, some kind of blue crystal and you're buying 3 kilos of it, it's 3,000 grams. So, and then there's mega, which means a million. And there's also all those smaller than 1 prefixes like milli, millimeters, and centimeters, and stuff like that. But we're just going to deal with the large ones. And then there's giga, which stands for billion. And then there's tera, which stands for trillion. And I don't know what's after trillion. Now, in computer terms, this is what it means to math people and physics and chemistry people. These are known as the SI, System International Counting System, where you use these Greek prefixes to multiply things by 1,000 or a million or billion or whatever. But in computer terms, this means 10 to the 2 to the power of, gosh, what is 124 in binary? Okay, 2 to the power of 6, 2 to the power of 16. Nope, that's too large. No, it's not. 2 to the power of 32, 2 to the power of 48. I'm just taking guesses until I get 2 to the power of 64, 128. Oh, for Pete's sake. Not getting there fast. 16 to the power of 2, 16 to the power of 3, 16 to the power of 4. I'm still not getting there fast. 16 to the power of 8. 16 to the power of 16. I'm doing times. No wonder it's getting not going anywhere fast. I'll get there. There it is. There it is. There it is. Okay. Computer engineers redefined kilo to mean 2 to the power of 10, which is not 1,000, but 1,024. And then a mega was not a million, but it was 2 to the power of 20, which is, come on, Mr. Python, you can tell me. 2 to the power of 20, about a million, right? Close to a million. And then 2 to the power of 30, which is whatever. It's going to be close to a billion. No, 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 no. 2 to the power of 30. Oh, whoops. 2 to the power of 30. Right, that's close to a billion. So a rough estimate, and then whatever 2 to the power of 40 is. If used to be that you would buy some kind of hard drive. I bought a hard drive that had 40 megabytes in it. It's according to the 40 megabytes. According to computer engineers, that's equal to 40 times whatever that number is. There. It had that many bytes in it. And so then the marketers would say it had 41 million bytes or 42 million bytes. And so they played a little game where the engineers would design it in one counting system, you know, in the into the powers of 2, and then the marketers would report that and say that it was a 42 megabyte drive when it really was just a 40 megabyte drive, something like that. Where was I going with that? Okay, so a kilo effectively means 1,000. Nobody deals in kilos anymore because except for the drug buyers, because our technology has gone way past that, right? If you had a computer in the 80s, it was a Commodore 64, which meant 64 kilobytes. And you had a 512 kilobyte floppy drive or something like that. That was all 1,000 bytes. 64,000 kilobytes meant, or 64,000 bytes meant that it could hold, you know, a document that was at max 64,000 letters long, right? Once you type more than 64,000 letters, you filled up your computer's RAM. So, you know, you weren't going to be able to write War and Peace on it unless you broke it up into chapters and saved each chapter separately to a file, something like that. So then you bought things that had megabytes. My IBM PC in 1988 might have had a 4 megabyte well, it had 640 kilobytes of RAM because Bill Gates decided that 64 kilobytes would be the most that a computer ever needed. So, but you'd buy a hard drive for it, it might be a 4 megabyte drive holding up to 4 million characters. Now, 4 million characters sounds like a lot, but your music files nowadays are more than 4 million bytes long, right? You get a really good high resolution, of the newest, Taylor Swift song, and it's probably going to be about 6 million bytes long, which is more than the entire hard drive capacity of hard drives, in the early 80s, just to hold one Taylor Swift song. Pictures. You take an 8 megabit picture or a 16 megabit picture with your phone. You could only store like 2 or 3 of those pictures on a hard drive from that era. So mega means million, giga means billion. So nowadays your iPhone or your Android probably has 1 gigabytes or 2 gigabytes of RAM and then more of storage, right, of the hard drive space, except it's not a hard drive, right? It's still solid state, but you might buy 128 gigabytes in your, that's what they sell it by, right? My Android phone has 128 gigabytes and my tablet has 512 gigabytes. It's billions of bytes, so it can hold a lot of songs and a lot of pictures and a lot of apps and stuff like that. Okay, I wandered rather far afield, but I want you just to be familiar as computer people to know exactly what those words meant. Close enough anyway. You know that a kilo is now 1,000, and a mega is a million, and a giga is a billion. Now, some people hated the fact that kilo meant one thing to physical scientists and another to computer scientists, so they made up goofy prefixes. Instead of kilo, this was kibibytes. Kibi. And I don't even know what mega was called. Let's just say that it was called megabytes, something like that. And then gigabytes. This is close. We could look up kibibytes. That's the only one that I'm absolutely sure of. And now, did anybody ever start calling their computers, I have 4 megabytes in it? Nah. They just stuck with this. But this was like the, if you're a PhD level, computer scientist writing your paper to get published or whatever, you might have called it that. All right, that's rather far afield. So what do I want us to know about all this? I want you to remember the ASCII table. I want you to memorize. No, I'm totally kidding. You're not going to memorize the ASCII table. But I want you to have the idea that everything you type in your keyboard just comes in as a series of zeros and ones that ultimately looks like this, right? If I'm going to spell the word bad, B-A-D, it comes in as a 66, a 64, and a 65. We can get those values inside Python. Launch idle if you haven't. Go to the shell if you haven't. Right now I'm in the shell. And if you type ORD parentheses quote A, end quote, in parentheses, it says 65. That's the ASCII value of an A. So when you type in an A, the bits come down the keyboard cable to represent 65. And then if you save it to a Python file or a text file, then there's a 65 written in the hard drive underneath it all, because everything is just zeros and ones. So ORD of quote B, end parentheses, end quote, is a 66, right? One more. So if we went back to the ASCII table, we'd see that a 66 was a B. What if you want to go the other way? What if you have a number, an ASCII value, and you wanted to see the English text letter, right, that it matched with? You can use another function called CHR. CHR of 67, right? 67 is going to be the next in our little value, in our little series, is a C. And it just so happens that to go from uppercase letters to lowercase letters, you add 32 to it. So if I took that 67 and I added 32 to it, I think that would be 99. So CHR parentheses 99 in parentheses is a lowercase c. Those ones, like if we ask the user to type in, their birth date, and they type in 1967. Well, what's a ORD parentheses quote 1 in quote in parentheses? That's a 49. And then what's a 9? ORD parentheses quote 9 end quote in parentheses 57. So if they typed in 1999 as their birth date, it would say 49, 57, 57, 57 as the zeros and ones that were coming to us. So 49, 57, 57, 57 is what the computer gets when we type in 1999. Each one of those being 2 bits, or, you know, 1 byte of information. That's kind of a byte, that's kind of a byte, that's kind of a byte, and that's kind of a byte. And if it was represented in hexadecimal, it'd be different, but whatever. So that is why when you ask the user for a number, we can't do math with it, right? We typed in for their birth date, and then we wanted to calculate their current age, so we took 2019 minus 1999, something like that. And we can't multiply that by 2. We can't, you know, add something from it. It's a series of bytes that does not, it's not a number. I mean, yeah, it's kind of a number in a way, but it's zeros and ones, and it doesn't represent a math number that we can do math with. That's why we have to use that float function, or that int function, to turn these series of ASCII characters into numbers that we can actually do math with. Because 1999, there, now that's a real number, right? This is just a series of ASCII characters, ASCII values, right? That's what they typed in. The computer got 4 bytes in a row. It turned it into 1999 when it got displayed on the screen. But that's just happenstance. It could have represented anything there. This had to be turned in, these series of bytes had to be turned into a real number for us to do math with. And that's why we use those float, or those float or int versions. Because if I took quote 1, 2, quote, and I tried to divide that by 4, I can't do that. This is just a string of ASCII characters, a string of bytes that is not a number that you can do anything with. But if I type in int or float, parentheses quote 12, end quote, in parentheses divided by 4, now I can do math because this was converted into a whole number. Hope that kind of, at least 25% made sense. If you got 10% of it, that's good. If you got 25, that's even better. If you got 100% of it, that's awesome, right? The stuff that I want you to know, we're going to come back and revisit as a worksheet just because I want you to memorize it. But until I tell you that, right, in 1 year, and hopefully it bounces around long enough for some of it to stick. Why don't we go ahead and make a little note of what we're going to revisit when we do the worksheets. Convert binary to decimal, just like we did, right? That's why I actually had you type it where you typed in 16 plus 4 plus 2 plus 1. That definitely is going to be on our worksheet. And then convert hexadecimal to binary. Now, I didn't make y'all do this, but that was the one where we were just using the lookup table. Where'd my lookup table go? Oh, great. I probably have 2 different files going on. Yeah, somewhere. Where'd my lookup table go? I know I typed it, right? That one with A, B, C, D, E, F, G. Oh, this one. Right. So I gave you some series of numbers in hexadecimal, like C, A, D, E, and we just converted it. Actually, we didn't do that. We better do that. Let's say we have the word 9012 in hexadecimal in base 16, and I wanted you to convert that to base 10. Well, what is a 9 if we just want the zeros and ones? A 9 is a what? Yep, 1001. And what is a 0? All zeros. 1, 2, 3, 4. What is a 1? If we go from this column to this column, it's a, yep, 0, 1. Let's make this longer, just because we're having a great time. And then what's a 2?
0, 0, 1, 0.
Yep, 0, 0, 1, 0. And what's an A?
1, 0, 1,
1, 0, 1, 0. And what's a C?
1100.
Yep, 1100. I mean, I'm trusting you. I'm not looking up at this point because y'all were being certain about it. So that is, this number here is equal to this number in binary. So if you had this number typed in, these ASCII values, whatever, this numeric value, then underneath it all, the computer treats it as those zeros, those numbers as zeros and ones. And if I was going to write this down, I would break it up like that, just to make it easy to spot. Make sure I got it right. One more thing, and then we're going to go and maybe take a break. My brain needs a reset. What if we need to convert hexadecimal into binary? Something like that. If we need to convert from hexadecimal to decimal. Say we had this string, FF. We asked the user to type in their age, but for some reason they were going to type it in hexadecimal or something like that. You can do int parentheses quote and then the number, like AF end quote in parentheses, but you can say what base. I want base 16 rather than base 10. It defaults to base 10, but if you type in a base there, then it turned, okay, so that's a 175. What about an F? int parentheses quote F end quote in parentheses. Great, but I forgot something. I forgot to say it was base 16, so it counted as an error. int parentheses quote F end quote comma 16. According to our little ASCII chart, our little lookup table, and F is in fact a 15, right? And then the highest that can be held in 2 bytes, since we have 4 bits. Well, in 1 byte, because we have 4 bits. In 4 bits, that's 2 ASCII, 2 hexadecimal characters. That'd be the highest that can hold. And then we get R to 255. So we have a function available to us which can convert from base 10 to base 16. Or it could be base 8, or it could be base 3. What if we had this number? int parentheses quote there, right? And we wanted to convert that into binary. We would use base 2. And that's the base 10. That's the decimal equivalent of that number in binary. Let's break and come back like at 1:30. Too many numbers. If you have the idea of zeros and ones, you have the idea of the ASCII table. Can't believe I have two notes going on. I'm gonna have to, okay, so convert binary to decimal, convert hexadecimal to binary, convert ASCII or convert text to ASCII, and convert ASCII to text. That'll be on our worksheet that we work on together. It's not there. Those are the 4 things that we're going to cover in our worksheet, which I don't have ready for us today. So that'll be like Wednesday or something. Then you can forget about it until the exam. And if you don't remember how to do it on the exam, I'll probably get on the board and show it to you right on the spot. There'll be 3 points. I just want y'all to have the idea in your brain that this stuff is possible and have half enough clue of how to do it. If you have a total clue, that's even cooler. All right, guys, we're going to... Oh, man, I left the recording going. People at home are going to have a 10-minute break in the recording. Oh, well. We're going to jump a couple of weeks ahead in the schedule just to show something, and just a sec. Just to introduce y'all to the idea of arrays very, very briefly, so that when we come back to it, it's a lot more familiar. Yeah. I am so sorry. Pardon me. You're my teacher's pet now. You're in brownie points. See, I should bring cookies. All right, so let's make a new file. I believe we're on lecture E. Don't save it in a Python directory. I always say that just because it's important. And by the way, never name your file turtle or math if you want your future assignments to work. Just never call it turtle or math. Lecture E. Alright, so this is what's known as an array. An array is a sequence of numbers. Like this. Your test scores. So we created a new file, lecture-e.py. We're going to calculate our test score average, or just a sum of the test scores. I made a 90 on my first exam, a 95 on the second, and 100 on the third. Alrighty. Print, parentheses, quote, first test equals, end quote, comma, scores subscript 0 in subscript. And when I say subscript, I mean square brace, and by square brace I mean the character next to the P on the keyboard unshifted. And then we're going to do second test equals scores 1 and third test equals scores 2. That's worth copying and pasting to save myself some typing. So I'm going to highlight that line, right click, paste, paste it twice. So first test, second test equals scores 1, and third test equals scores 2. There we go. My first test was a 90, my second test is a 95, my third test is 100. So what do these subscripts mean? We're calling them subscripts. Well, computers start counting things as 0, which is why we had a homework 0. And that's why all of our odometers started with 0 rather than 1. So this is the first element of this array. Scores 1 is the second element. Scores 2 is the third. And if we had 100 elements, they would go up from index 0 to index 99. Now, if there's 100 elements, why did I say 99? Because notice this. What is the length of the scores list? 3. 1, 2, 3. What's the highest index? 2. If we had 10 items in our scores, the indexes would be 0 through 9. And again, if we counted them out on our fingers, 0 through 9, well, let's just do 5, right? 0, 1, 2, 3, 4. So if there is a list of 5 scores, then the highest index is 5. The lowest index is 4. Let's print out the length of the scores list. Print, parentheses, quote, length of list equals, end quote, len, parentheses, scores, in parentheses, and then we have to have one more in parentheses to match the beginning one. There we go. One last little thing, or maybe two last little things. Let's get the sum of the scores. Next line, total equals sum, parentheses, scores. That goes through the array and adds them all together. Now notice the color of the word sum. That means that that's a function. len is also a function, just like print is a function. And you know what? I love the word sum. Whenever I'm calculating something, I want to type this, don't. Sum equals 1 plus 2 plus 3. That's a bad idea because sum is a purple word. It would still work in this language, but it erases the sum function. I could no longer use the sum function for the length of that program if I do that. All right, I'm going to erase that. All right, now we're going to print all these scores out with a for loop. Not that we've talked about for loops, but a for loop is just a way of stepping through a series of values. You can have a for loop that counts from 1 to 10. In this case, I want a for loop that prints all the numbers out. So after total is equal to sum parentheses scores in parentheses, I'm going to have for v space in, the word in, space scores colon, just like our if statements that I think we've used maybe once or twice. For v in scores, hit enter, and then it better be tabbed over. Print parentheses v in parentheses, and then back tab back to the last margin, to the leftmost margin. All right, and there we go. It printed them out again, right? But it printed them out in 2 lines of code, right? So if we added a whole bunch more scores, right? Comma 80, I didn't study enough for that one. Comma 0, I skipped that day. Comma 100, comma 100, comma 99, right? I just modified my scores list. I added some more so-called elements to the array. This is an array. So I put hash array at the end of it. Now these 3 print statements are going to stay the same. It's going to print 90, 95, 100, but it's not going to print out all the elements of the list. I would have to go and copy and paste, right? Print the 4th test equals, 5th test equals, 6th test equals, and so on. I'd have to modify the code here in order to handle all those new elements. But I don't have to modify the code to handle the new elements with my for loop. The for loop expands its capacity based on the length of the list. So it's going to print out all the scores down here. You know what? I forgot to print the total. Why don't I print the total? So the last thing after the for loop before we drop the idea of arrays is printing that sum. So print parentheses quote total equals end quote comma total in parentheses. So you see what I mean? The first 3 elements, sorry, I can't get it all on one screen. I typed too much. The first 3 elements, elements 0, 1, and 2, were printed here, but it didn't print out the entire list of scores. However, the for loop did print out the entire list of scores. So loops are how you're going to be handling arrays most of the time. They're kind of like hand in hand. If you have an array, if you have a list of values separated by commas, then you're probably going to have a loop to add them up or to print them out or do something like that. Programming wise, if you get the idea of how to write your own functions, how to handle arrays, how to do loops, and how to do if statements, by the time you get those 4 concepts, you're a programmer. If you get those in the first 3 weeks, great, you're going to learn a lot more in it. By the end of the class, if you know those 4 things, then you can walk out if you're thinking that you have a programmer's way of thinking about things. If statements, defining functions, which the book calls modules, arrays, and lists, those are really the fundamentals of programming. Now, yeah, computers are written to do math, and so, you know, we're going to be doing math all the time, but you already knew how to do math, right? Expressing it in computerese is a slightly different matter, but you have the idea of math, right? The idea of loops, well, you kind of have the idea of loops, right? If you're washing your dishes, pick dish up, wash, put in the dry, you know, the dry bin, and you keep doing that until you run out of dishes. That's all the for loop is doing, is it's stepping through. So the first time, v equals 90. The second time, V equals 95. The third time, V is equal to 100. And that's why when we run it, we see it print out 90, 95, 100, and so on all the way to the end. Okay, now we're going to write a fancy statement. The subscripts PS, PTS. I don't know why I flaked on that. Subscripts, like you're a script writer, for an array of length 10 are 0 through 9. So ditto for an array of length n are 0 through n minus 1. There, we got all fancy. If you have an array of 100 elements, the valid subscripts are 0 through 99. I think I'm going to add a comment above the for loop. Using a for loop to, quote, iterate, parentheses, step through, in parentheses, the array. That's what we did there. I think another textbook, maybe this one calls it traverse, or quote, traverse. Those terms are interchangeable. Iterate is more commonly used in textbooks, but traverse is just as accurate. Ooh, I'm going to modify that. Step through the, quote, elements, end quote, of the array. We have to learn the jargon so that we can press our partners and our friends and our children about what we're doing. Or parents. Yeah. I'm going to iterate through the dishes today. I'm iterating through this book, reading it word by word. You can also iterate backwards, right? I wouldn't read a book like that. If you're going to iterate backwards for an array of length 10, you would start off at element 9 and you'd go down to element 0. All right, we're way ahead of the textbook, so we're going to open up the textbook and pick back up. Well, I guess since I have my notepad open, I'm going to add those two websites we used. The two websites we used, this is in the notepad file, were ASCIItable.com and hexed.it. Just so you can play at home when you're bored. Go there on your phone. I wonder what that would look like on a phone. At hexed.it. Oh, I'm going to veer back towards using hexed.it just for a second because we could upload a different file other than a programmer file rather than a text file. Like I could find an executable file, a .exe, or I could try to find a picture. So if I do open file and I find my screenshot and I double click my screenshot, see there's no text in there. Oh, that's not quite true. There's a little bit. The format of the file is in so-called PNG, Portable Network Graphics or something like that. And then we see the term HDR, which stands for header. And then we see a whole bunch of gobbledygook. That's because pictures are stored, you know, in zeros and ones, so that each pixel it can be a different color, or a series of pixels can be a certain color, or whatever. Same with music files. If we found an MP3 file, there'd be some English text in it. The name of the song, the name of the album, the name of the artist, all those tags you can edit, right? And then I guess if there's some lyrics attached to the file, Yeah, you can do that. If you have iTunes or some editor, you can copy and paste the lyrics in there so it show up on your phone, or if you download them or something like that. Those would be in text, but then the rest of the music is stored as a series of numbers, just because, you know. It could be that you'll get to the point where you're writing a program and you need to understand how to create a header for a file using this kind of binary format. And you'd probably use a hex editor to look at it during part of the debugging process. All right, just wanted you to see that. Let's go find an executable and then we'll be done using the hex editor. All right, executables, program files 86, Microsoft Office. I'm going to find an exe in here, right? Well, there's one, but there sure aren't a lot of exes in here. I was expecting to see a whole bunch more. All right. We see something that says this program cannot be run in DOS mode. Well, if you install a DOS emulator on your computer and you ran it, it would give you an error message. Who remembers DOS? It was the operating system used in the 80s and in the 90s before the invention of Windows something or other. I forget. Windows 95 still used DOS, maybe Windows 98, and after that, they no longer use DOS. Your DOS games like Wing Commander or Zork and stuff like that would not have had this message in here. This program cannot be run in DOS mode. Then if we scroll up and down, we might see some more text. Whoops, I saw some. Get file version, info size, get file. So there is some text in there, but most of it's just all the zeros and the ones, all the numbers that tell the chip what to do. I did get up there and draw a chip in a box, a dude named Chip, right? Yep. Okay. All right, so the subscripts of an array linked 0, 10, or 0 through 9. Let's find our current PowerPoint, or if we have to download it. Looks like we have to download it. Thought I had Canvas open. Probably need it. I need to get to the point where I only have one browser open. It confuses me. All right, canvas.rose.edu. Modules. That's the one thing I liked about D2L is I was able to list submodules in such a way that they showed up really easily so that you would not have to click on that and then find the appropriate thing to expand. That's all right. There's a lot of things I like better about Canvas. Elements of high quality programs. I really thought I'd open this. All right, it's not 999 kilobytes long. I'm suspecting that this is not right. Maybe I tried downloading it again. I'm suspicious. Oh, are we just not going to open my PowerPoints? Okay, now it's gone. Isn't it funny that no matter how big, how fast your computer is, the programs expand to match it so that they take just as long to open applications? Pretty cool that phones open their applications so fast, because desktop computers, although they run in the gigahertz speed, still are slow because the programs are so big. All right, elements of high quality programs. Declaring and using variables and constants. We've already used variables, x equals 3. Performing arithmetic operations, the advantage of modularization. Now, Donna Wilson and I agree that we should not be hitting modularization until like chapter 5, but whatever. I guess it's one of those things where if you hit the concept early, it's better. Hierarchy charts, we're going to talk about that for 5 minutes and I'm never going to mention it again. And features of good program design. Alrighty, understanding data type. Data types, we've talked about this. There are 3 data types we've used so far. Floats, ints, and strings. That's important enough that I'm going to go ahead and add it to my program. So now that I'm going to be talking pure notes, I'm going to start the green text again. Quote, quote, quote. 3 data types so far, and then there's a fourth one called Boolean. But data types, int, integers, are whole numbers. If you try to store a float into an integer, it's just going to round it down. Now in Python that's not true. If you try to store a float into an integer, it's going to erase the int and then make it a floating point variable to hold the floating number. But still, we have to teach to the text as well. And then a float is a floating point, meaning it's got a decimal. And then there's a string, and I'm going to put quotes around it because that's how we define them in the homework, in our program. String of characters, like what you get from the keyboard. You don't get integers and floats from the keyboard. If they type in something, it's a string, and then we have to convert. So when we use when we use the input function to get data from the keyboard, we get a string which must be converted to an int or float to use for math or whatever. Now if it's not a number, you don't have to convert it, right? If it asks what is your name and you type Donald Duck, we don't have to convert that to a number. So a variable is a named location in memory that we use to store a value that holds a value, like x equals 3. We created a variable. The name of the variable is x. The type of it is based on the data type. What is a whole number? What data type is a whole number? Look up here to our list of data types. The type of a whole number is an int, right? And then the value is 3. Now there's a fourth component of a variable, which is the memory address, but we don't know what the memory address is. So the memory address is whatever. And I think I'm just going to put that in parentheses because we don't have a way of figuring out what the memory address is. So this is a definition for a variable. The textbook may have a slightly different definition. A variable, I'm changing this text just a little bit. So now I'm going to list the 4 components of a variable. It's just these 4 things. 4 components of a variable: the name, the type, the value, and the memory address, which we don't care about. Focus on the first 3. If I had a test that asked what the components of a variable were, I'd say what are 3 of the components of a variable, and I'd want you to type name, type, value. Now if you typed name, type, memory address, I'm not going to count you wrong, but these are the important ones, right? Because we can track these. It's up to the computer language to pick the memory address. We don't specify that this number or this Donald Duck gets stored in byte number 1,000,000,2037 in our computer. The program picks that for us automatically. Now in the 50s, the 60s, you may actually have picked the memory address, but computers were far simpler back then in some ways, which made programming them far harder in others. Your program had to keep track of the memory addresses. Nowadays they don't. All right, so focus on the first 3 period. Those are the idea of a variables. Those are the idea of variables. We have different types. Y equals 3.0, 3.9. Name is Y. The type is float because it's got a decimal point in it. And the value is 3.9. Now, once you declare a variable, you can use it for math, right? You could say z is equal to y times x. You could erase it and replace it with something, right? You could say x equals x plus 1. It would add 1 to x and store it back into x. Now, if it's a so-called constant variable, that means that once it's declared, it can't change. A constant is a variable whose value cannot change. Once you set x equal to 3, the program can't change it to 4. Now, Python doesn't have constants. There's no such thing as constants in Python, unlike a lot of other languages. We simulate that by saying if the variable is uppercase, then it's a constant. In Python, we say that if a variable is uppercase, it's a constant. Kind of like a gentlewoman's agreement. We all shake hands and say, okay, if I'm looking at your program, I'm never going to change the value of x in it because it was capital X because it was declared as a constant, even though it's not true in this particular language. And the book says that too, that if you name a variable in uppercase, it's supposed to be a constant. An example of a constant, good old pi. We love circles, so we have to learn how to do pi. I'm going to say capital PI equals 3.14159. Good enough, right? Yeah, it's infinitely long, and I'm not going to type an infinite number of digits. And then, so the circumference, which I'm just going to spell circum, save myself time. Circumference, heck, let's do area. That's even easier to type. Area equals pi r squared. So pi times whatever the radius is, 5 star star 2. Area equals pi times radius squared. That's what I was doing there. Pi is a constant, meaning that my program should not try to change the value of pi. If I did pi equals pi plus 1, well, we've broken the universe, right? I can no longer calculate areas or circumferences or whatever, volume of a sphere, because if I change the value of pi halfway through the program, all my subsequent calculations are going to be wrong. Now, we're probably smart enough to know that we should not use the pi variable to hold anything else. But there may be other variables that look like we ought to be able to change them. Max underscore length of array, right? Maybe it's really important that that value does not change, in which case I would declare that variable. I would give it a name that was all uppercase letters, because part of programming is not only to get the program to work, it's to write the code in such a way that if you edited it later, you would be able to make changes to it without making mistakes. Or if you're working on a project with somebody else, they could look at your code and they could edit it without making mistakes. And it sounds stupid, in a way. Well, I'm going to declare something as a constant to make sure I don't change it later. Well, I know I'm not going to change the value of pi, or I know I'm not going to change the value of max array length. Well, you may not know that when you come back 2 years later. You may think, okay, if I increase max array length, I'm going to make my program more powerful, and it's going to be able to hold a larger series of numbers. That may not be true. Or if you give this to somebody else to edit, then it may not be true. I mean, they need to sit down at it and know that that value should not increase. So they better not change it, and the way we communicate to that to them is we declare it as a constant. Now, in other languages, you have a keyword that means constant, like constant x equals 3, semicolon. That's like the C language or C++, except comments in that language are done like that. Or in Java, final x equals 3. I don't know why I didn't pick the same word, but that's how you do it in Java. And there may be other ways of doing it. There may be other keywords, but those are the ones that I know. You don't have to memorize those. Just know that Python doesn't have the equivalent. There's no word that means const in that language, so that's why we deal with the uppercase letters. And you should do uppercase letters anyways. Tell you what, if we're going to make this exactly correct for those languages, we would use uppercase letters and we would give them a type. Because unlike Python, in those languages, you have to give the type when you declare the variable. And you will see code examples like this in the book. That's why I'm taking the time to type this out. I don't want you to memorize it unless you take those languages, but I want it to be familiar for looking at the book. Const double capital PI, not OU. Weird that those are next to each other. PI equals 3.14159. And then for Java, final space double space PI equals 3.14159. That's how you do it in that language. In Python, you just go pi equals 3.14159. And that's good old Python. Good new Python. Python was invented after these languages, and so it's kind of streamlined. And it's just, it's a powerful language. It's not dumbed down. It's just streamlined. It's got a better syntax because the guy put some thought into what makes the other languages hard. I'd rather do this than this, right? This took a lot longer to type. The syntax was a lot more gnarly. So, declare your constants with uppercase letters. Now that doesn't mean I'll never use uppercase letters for anything else, because if I'm trying to use L as a variable name, I'm going to make it a capital L, because otherwise it looks like an I or a 1 on your screen. But for the most part, I'm going to make all my variables lowercase, just to match that, unless they're supposed to be a constant. All right. So programming languages have to support these data types. Well, I guess they don't have to, but they support numeric data types and strings. Now, it's nice if they support more than that. And then numeric data types are broken down into floats and integers. The computer treats those as different things inside. We may think that if you say x equals 3.0, that that's the same thing as 3. That 3.0 is the same thing as 3, because that's the way, it worked in math, up until now. If you typed in 3.0 in your calculator, it treated it as 3. But the computer uses completely different circuitry, completely different transistors or whatever are parts of the chip anymore to do integer math versus floating point math. It used to be that you had to buy what was known as a floating point coprocessor to plug into your PC in order to get it to do floating point math, which is absurd, right? But if you were going to play some kind of game that did, complex math to display, space in 3 dimensions or something like that, it had to have a floating point coprocessor. And if it didn't have one, you had to buy one to install it. We're talking early 80s. Integer math is way faster than floating point math. But nowadays, computers are so fast that they can do floating point math lickety-split. However, they sure can do it a lot faster if you buy some powerful Radeon card, right? Those things are optimized to do floating point math incredibly fast. And they have billions of transistors. It's funny that your video card is probably more powerful than your computer. That's why you can buy a computer for like $300 or build a computer for $300. But if you buy an incredibly powerful video card, it can cost $800, right? And the computer consists of the whole thing. The video card is just optimized to do one thing. So the people who do so-called Bitcoin mining, which is trying to calculate new Bitcoins, Bitcoins are weird. They're a form of currency that's just somebody invented, and nobody manufactures Bitcoins. They're just random numbers that are calculated. and all the easy numbers to calculate for Bitcoins have already been solved. And so now it's incredibly difficult to come up with new Bitcoin values. So people build computers with multiple video cards, and they use the video cards, which do the math insanely fast, in order to do the calculations to try to be the first one to get that specific Bitcoin number. And then there are these things called Bitcoin farms, where people, you know, will hook up 1,000 computers, each one with multiple video cards, trying to generate Bitcoins as fast as possible. You know, and it costs a lot of energy and a lot of air conditioning and room and, you know, expenses. So Bitcoins were, you know, kind of a big deal. People were, you know, the value of Bitcoins were going up astronomically, and now I think they've kind of plummeted and stuff like that. Yeah, yeah. And so, you know, maybe their investment kind of didn't pay off. But anyways, so floating point math is slower to the computer. It's treated differently. In this language, floating point and integer math is done interchangeably. For the most part, we don't have to worry about that. And the reason why the programmer didn't make a distinction between the two, for the most part, is because it's easier to not have to worry about it, and usually you don't care. If you do care, you use that int function to force the issue. So we know it. Okay, constants. A numeric constant is a number only, and the value should not change. A string constant is an alpha numeric value, right? It's got, it could, if you ask the user to type in your name and you type in William space 3 because you're the third, it's got letters and it's got digits, so it's called alphanumeric. And in that case, the strings are enclosed in question marks, right? So there's a big difference to the computer. If you do n equals 3, n equals 3.0, and n equals, why am I not typing this in my green text? Go back. There we go. If you say n equals 3, n equals 3.0, and n equals quote 3, those are three completely different things as far as the computer is concerned. And if you need to deal with this thing as math, you have to convert it. So that's a string, that's a float, and that's an int. For the most part, we're just going to use floats for math just because it's easy. What do I mean by that? If we ask the user to type in a number and they add a decimal point, we don't want the program to crash. And if you try to convert a string to an int and there's a decimal point in it, the computer's going to crash with a runtime error. So if we make it a float, we let them type in data in a more flexible format. It's less error prone. That's the only reason I say that we're going to be using the float keyword more than the int keyword. The int keyword would work, but only if we trust the user to never type in a decimal point. For year, you could use int because nobody says that I was born in 1991.3. At least nobody that I know. You'd have to be a real nerd to do that. All right, working with variables. And I'm a nerd, so I'm not using that term as an insulting thing. Variables are name memory locations. They have a data type, they have an identifier, which is the name, and they can have an initial value. Now in this language, they always have an initial value, because when you create the variable, you give it a value. But in some languages, you don't give an initial value. Remember when I was declaring pi up here? I didn't have to, where did that go? I did not have to give it the value of 3.14159 here. I could have just said double space pi and then use it later. In that case, it's called an uninitialized variable. Now, this language doesn't support uninitialized variables. But I'm going to give an example just so that we know. Int I, this is an uninitialized, I spelled it wrong, variable, not, this does not work in Python. Not a thing in Python. Every time you declare a variable, you have to give it a value. That's an example of C or C++ or Java. The above is C++ syntax or Java syntax or whatever. The book talks a lot about uninitialized variables, so that's why I'm mentioning it now, even though our language doesn't support it. The book does talk about Python, of course, as of this version, but they also have to talk, you know, even though Python's a good language, you can be sure that 80 to 90% of the programs out there or more are written in other languages that do care about things like uninitialized variables. Python's getting more popular, but it's not fast enough to write like video games or word processors or stuff like that in. Why is it not so fast? Because it's written in a way to run on multiple platforms. I talked about that emulator, that engine, that shell that Python is processed on, and that shell means that the program has to be turned into machine language every single time it runs. Whereas if you write a program in C, C++, it's turned into an executable by the programmer, and then you give that executable to a user. That work's already been done, so it runs really fast. Notice that this says identifier and then name in parentheses. I guess I should scroll back up to where I said the 4 parts of a variable. I'm going to put name parentheses identifier just because the book called it an identifier. I'm going to veer away from the lecture because if we don't actually do some sample code, then I'm not going to really be able to give y'all any homework. And you're going, well, that'd be okay, but nah, we really need to do some programming. All right, what if we're going to ask the user for a value or 2 values or 3 values, and then we're going to use those values in a calculation? So we're going to calculate the recommended maximum aerobic heart rate based on age. The formula for that is heart rate equals difficulty times 220 minus age. I don't know where that U came from. Difficulty times 220 minus age. Where difficulty is something like 0.5 to like 0.75. You really should not, unless you're, you know, a supreme athlete. You know, for cardio, you don't want to go 75% of your utter complete max heart rate. If you get on a treadmill and you get heart rate at 220 or whatever, you're just about to pass out. So you don't do that. Okay, so we're going to have to ask them for 2 things. We're going to have to ask them for their age and for the difficulty. Then we can calculate HR. Then we calculate HR, heart rate, and display it. That's what our program is supposed to do. So if you get on a treadmill, and it's one of those nice fancy ones with a computer built in, then there's probably a way to program in your age, and then it'll try to show a little meter showing the difficulty, right? You know, and it goes into the red if you exceed, you know, 75% or whatever. These are percentages just expressed in decimal format, right? 50% is 0.5, 75% is 0.75. So we have to ask for the age and the difficulty. If we were going to pseudocode this program, pseudocode, we don't write pseudocode if we actually expect the computer to do it. But we write pseudocode in order to understand the logic. All pseudocode starts with the word start. And then everything is tabbed over. Even if that's not true on the computer, pseudocode is its own thing. Just like instructions to go to Walmart, and then the detailed instructions are different, right? I could say, you know, go forward 1 mile, turn left on, you know, Sooner, turn right at Walmart, right? That's enough. But if I was going to program a robot, I would have to get like the number of feet or the number of inches it was going to go forward, and I have to give very specific commands. Okay, so start. Input space age. Input space difficulty. Calculate HR, and the formula, I'm going to put that as a comment, even though comments are a weird thing to include in pseudocode. Set space HR equals, why don't we just call it diff? But let's add a comment as to what that is. Difficulty. Set HR equals to diff times, parentheses, 220 minus age. Now 220 is what's known as a magic number. Why is it called a magic number? Because we have no stinking idea really what it means. Just some scientist, some researcher made it up. So we might want to declare a constant to hold that. We're not going to bother. Just introducing the term magic number. I probably have already mentioned it, mentioning it again. And then output HR. For my comment here, calculate HR, I'm going to put parentheses heart rate, just to remind myself what HR is. And then I'm going to back tab and I'm going to put stop. Now that's the pseudocode for our program. Now let's write a Python program. Python programs don't begin with start and stop, and they're not all tabbed until they hit an if or a while statement or something like that. So they look a little bit different, and people sometimes get a little bit confused. They mix the syntax together. They're just two separate things. We have to kind of learn both of them. The book talks a lot about pseudocode. We'll have a lot of opportunity to read about it when you read the text. I don't give daily quizzes over reading assignments. I probably should, because I know a lot of people don't read the text until they need to take the exam. Whatever. Can't make you read it. Recommended. All right, input age. Okay, I'm going to stop my green text with another series of 3 quotes. And I'm just going to change these pseudocode statements into programming code. And I'm going to put the pseudocode statements as comments, right? So I'm just going to highlight that, copy it, and make it a comment. Or it would not have taken that long just to type it right. Quote, or hash, input age. Age equals input, parentheses, quote, enter age. Space, space, greater than, just because I like to show them where to type. End quote, in parentheses. And we better convert that to a number, or else we're not going to be able to do math. So, age equals float, parentheses, age. I am going to add a comment here. Convert input to a number. That's why we did that. Convert input, convert the string to a number. Anytime we do math, we're going to have to do that step. Not true of all languages. Some languages have a built-in thing that'll convert it as it's typed. Every language has its own rules and quirks. All right, we've done the first part. Now we need to do the input difficulty. So space input difficulty, or hash space input difficulty. Notice I'm using the comments kind of like chapter headers, right? Or you're outlining your essay and then you go and fill in the essay. My comments are going to kind of match my pseudocode. All right, so when we input the difficulty, it's going to be the same syntax. We're going to use the input function. Diff equals input parentheses quote enter difficulty parentheses easy equals 0.5 comma hard equals 0.75. In parentheses, couple spaces, a greater than just to tell them where to type. Now my message is going off the screen, so I'm going to delete a couple of spaces here and there to try to get it to fit. You don't have to do this, right? You have a tiny font. So after the greater than, in quote, in parentheses. Now, what do we have to do? We have to convert that to a number, so what am I going to type? That's not a rhetorical question. I want somebody to tell me what I'm going to type to convert diff to a float. Just like I had to convert h to a float, I have to convert diff to a float. So this, yeah, diff equals, what's the next keyword? Float, parentheses, diff. Now we can calculate the calculate the heart rate. So hash, calculate heart rate. Which we have a formula for if I scroll up, but I think I remember it. HR equals diff times, and I had more spaces than you have to, parentheses, 220 minus h. I guess that means that if you live to be 219, your pulse rate would never better exceed 1. Kind of kid. And babies' heart rate should never go above 200 when they're doing their weightlifting. What was the last thing in our pseudocode? Scroll up if you typed it in and tell me. Yeah, output. We don't have an output statement. We have a display, a print. I could use the word output. I could use the word display. I could use the word print in my pseudocode. I'm not real picky. Notice that pseudocode had the word set in it. I don't care if you leave the word set off, because when you type it in Python, you leave the word set off. I'm easier going on the pseudocode. I don't mind if you make it look a little bit different, as long as the commands are in the right order in your pseudocode, right? Because you can't calculate a heart rate until you have the age and the difficulty. Okay, so down here, output, parentheses, display, in parentheses, heart rate. We could make a really fancy message, like a 2-line message. Print, parentheses, quote. We've calculated your recommended heart rate. So there's supposed to be a space in there. Anyways, end quote, in parentheses. Next line. You know what? We could even speak good English and put a period at the end of it. Print parentheses quote, it should not exceed, end quote, comma. What is our heart rate variable? What did we store our calculated heart rate into? HR, end quote, comma, beats per minute. Or maybe just per minute. End quote, in parentheses. Now our program is done. All right. It's ready to run, in my opinion. I may have made syntax errors.
Yeah, on the
Enter age. I happen to be 90. What? Okay, I did something wrong. I have a whole bunch of junk up here from that array, that scores array. Enter age, 90. Enter difficulty. I'm going to take it easy, 0.5. And so I should not go more than 65 beats per minute, which is probably lower than your resting heart rate, really, but whatever. I love using a Fitbit, and it tells me that I've walked 1,000 steps even when all I did is get up and sit for a while. Seems a little sensitive. That's all right. Okay. So we've written pseudocode. We've written a program. I'll do a walkabout and make sure that everybody's got the syntax right, but I'm going to create the homework assignment first. Ask the user for the miles to travel. Ask the user for the hours for the trip. Calculate the MPH, parentheses, miles per hour, which is just one divided by the other, right? 60 miles over 2 hours is 30 miles per hour, 60 divided by 2. And display the MPH. Just do the pseudocode if you want. You don't actually have to write the Python program. So, write the pseudocode and, can't type, and if you want, the Python program that implements it. Python script that implements. All right, that may only take you 2 minutes, so we got to come up with some others. Ask the user for their height in inches. Ask the user for their weight in pounds. Calculate the BMI. I am going to give you this equation. Parentheses body mass index. The formula is BMI equals 703 times pounds divided by parentheses inches times inches. Why don't we just call it in, get rid of that parentheses and say inches star 2. All right, can I think of one more? Oh, and display the results. Index program, not index, compound interest. I need to remind myself of the formula. Okay. Ask the user for the initial deposit parentheses P. That's a good variable name just because all the formulas show it. Ask the user for the number of years, calculate the final money, the accumulated money, total money, parentheses A, because I think that's what all the formulas show. Yep. According to the compound interest formula, I'm simplifying it to make some certain assumptions. At 10% interest. So the formula is A equals, I have to cheat and go and look, P, your principal, star, one plus 0.10 divided by 12 in parentheses to the power of, let me look at the formula again. Doesn't matter how complicated the formula is. 12 times the number of years. So parentheses 12 times T. We're going to call T the years. I need to go back and add that to my comments. Ask the user for the number of years, parentheses T. And then display the results. Now again, if you want, just turn in pseudocode. You don't have to write 3 separate pseudocodes. You could just go from the top to the bottom. You're right. Solve all 3 problems at the same time. And I'll write these notes, a little bit prettier. I'm going to tab this over. A is equal to P star. I wonder if I could simplify 0.1 divided by 12 just by doing that calculation and changing it. But you can type that in. That's not any hard. Okay. So those are the 3 things that I want you to pseudocode out. If you feel like implementing it in Python, so much the better. If you're confused over the idea of pseudocode, open up your text, right? Search for the word pseudocode, read the text about it, load up the PowerPoint. There's more about pseudocode in here. Just open up the text and do a search and find pseudocode. Read up there. You don't have to do it as fancy as they do it. You don't have to declare your variables because our language does not declare our variables, and so on. Just do it like this. We did an example of pseudocode that matches the style of the format of the homework exactly, right? Where was it? Right there. This is a pseudocode right here. Way up there. So this is going to be what I want y'all to turn in. If you feel like writing in Python, so much the better. But I want the pseudocode. Got to do the pseudocode to get the credit. That makes sense? Sorta. Hopefully, sorta. If you have questions over it, I do recommend that you look at it tonight or tomorrow night so that you can ask questions about it on Wednesday, because we can always stay a little bit late. Let's make a Dropbox for Dropbox E, and I'll do a walk around if anybody got syntax errors that you want corrected.